The 19th International Physics Olympiad Year 1988 IPHO. Problem 1. Maxwell's wheel. Theory. Introduction. A cylindrical wheel of uniform density, having the mass m equals 0.4 kg, the radius r equals 0.06 meters, and the thickness d equals 0.01 meter is suspended by means of two light strings of the same length from the ceiling. Each string is wound around the axle of the wheel. Like the strings, the mass of the axle is negligible. When the wheel is turned manually, the strings are wound up until the center of mass is raised 1 meter above the floor. If the wheel is allowed to move downward vertically under the pulling force of the gravity, the strings are unwound to the full length of the strings, and the wheel reaches the lowest point. The strings then begin to wound in the opposite sense, resulting in the wheel being raised upwards. Analyze and answer the following questions, assuming that the strings are in vertical position, and the points where the strings touch the axle are directly below their respective suspending points. See Figure 19.5. Questions. Question 1. Determine the angular speed of the wheel when the center of mass of the wheel covers the vertical distance s. Question 2. Determine the kinetic energy of the linear motion of the center of mass, e, r, after the wheel travels a distance s equals 0.5 meters, and calculate the ratio between e, r, and the energy in any other form, in this problem up to this point. Radius of the axle equals 0.003 meters. Question 3. Determine the tension in the string while the wheel is moving downward. Question 4. Calculate the angular speed omega prime as a function of the angle phi, when the strings begin to unwind themselves in opposite sense, as depicted in Figure 19.6. Sketch a graph of variables, which describe the motion, in Cartesian system, which suits the problem, and also the speed of the center of mass, as a function of phi. Question 5. If the string can withstand a maximum tension Tm equals 10 newtons, find the maximum length of the string which may be unwound without breaking by the wheel. Solution to problem number 2. Solution to question 1. In this problem, it is easiest way to use the formula for the law of conservation of energy when the center of gravity of the wheel is lowered by a distance s. Its potential energy is converted into kinetic energy of translational motion plus rotational motion. That is, Formula 1 is true. Next, we note that the moment of inertia round the center of mass I for the wheel is equal to m r large squared, and the kinematic condition linking translational and rotational motion gives the ratio v equals omega r small. Substituting these two expressions into Formula 1, we obtain Formula 2, where omega is calculated by Formula 3 and is equal to 52.1 radian per second. This was the solution to question 1. Solution to question 2. The kinetic energy of linear motion is given by Formula 4, which, when converted to known and calculated variables, gives 4.9 by 10 power negative 3 of a joule. The kinetic energy of rotational motion is given by Formula 5. Thus, the ratio of the kinetic energies of linear and rotational motion, after simplifications, is equal to the ratio of the squares of the inner and outer radii. Formula 6. This was the solution to question 2. Solution to question 3. In question 2, we found out how angular velocity depends on the distance traveled. This was Formula 6. Rewritten it here. Omega is equal to the following expression. Then the linear velocity downwards v will be omega by r small, and v squared will be expression 7. But on the other hand, v squared is equal to 2 by a by s. Formula 8. From this we get expression 9 for the linear acceleration downwards. This is Formula 9. Newton's second law through the formula 10m by a equals mg minus 2t gives us the final answer for the tension of one of the two threads in expression 11. This will be 1.96 newtons. This was the solution to question 3. Solution to question 4. After the entire length of the threads has been completely unwound, the wheel continues to rotate about the point O, which is at rest for some interval that will be discussed. Let omega be the angular velocity of the center of mass, about the axis passing through the point O. And the angle phi is measured from the horizontal, as shown in Figure 19.7. Then from the law of conservation of energy we have Formula 12. Here Ia is the moment of inertia about the point A. Formula 13. it follows that omega is expressed as a function of the angle phi through formula 14. To plot the angular velocity omega versus angle phi, note that r small is much smaller than the height h. Thus, formula 14 with a known approximation is transformed into 15, which is a shifted sinusoid. Figure 19.8. The velocity of the center of mass is calculated accordingly by the formula r small by omega, which leads to formula 16. This was the solution to question 4. Solution to question 5. It is obvious that the maximum tension of the threads will be in the position when the center of mass is at the lowest point directly under the axis of. There, both omega is maximum, and the force of gravity, with the centripetal force are directed strictly vertically. Thus, Newton's second law gives the expression to Tm is equal to mg plus m omega squared by r small. Formula 17. From which we obtain formula 18. From here, the maximum length h is calculated by formula 19, and is equal to 4 94/100ths of a meter. This was the solution to question 5, and here we finished discussing problem 2.